All right. So thank you all for coming for the 2021 Bullitt Lecture. We're thrilled to have a program. And thank you for Laurie Watkins for sponsoring this event together with the Society for Physics Students and the Reich Planetarium. So thank you all for contributing. And we will start with the Bullitt Scholarship and Bullitt Prize, and then we'll hear from the Where Is Everybody, which I realize is quite an apt title, but I know that this is a choice. So thank you for coming. We'll start with the Bullitt Prize for Best Paper and a Bullitt Scholarship. So could Luke Reeves, Ren Porter, and help me here, Jerry. John Pritchard. Thank you. I'm terrible with names, and it hasn't gotten any better in the last year. So could you all come over to the front, please? Can you take a picture? Oh, cool. Yeah. Hello.
Yeah, we're supposed to get the U of L photographer over here to, take the pictures.
Well, we'll send them over.
Okay.
That's the beauty of digital. So we have, to start with, we have a shared best paper between John Pritchard and Ren Mullins. You both submitted excellent drafts of paper that look like they're almost ready to go. So let's see if we had a little watermark here. This is for Ren. So Ren, we can actually get your...
Congratulations.
Thank you.
It's my grandfather.
Thank you.
And John Pritchard,
Paper.
and
Okay.
best paper.
Best paper.
Yeah, they were. We got a tie.
Congratulations.
And then Luke Reeves for the scholarship, for Bullitt Scholarship. So congratulations.
Memory of my grandfather.
Yeah. So let's. So we all sort of
Pose
bunch
the
in
photo.
together. Yeah, a little bit. So we can have a pic. Are we all in the picture now?
Yeah.
Thank you.
Thank you so much for
Congratulations. to the award.
everybody who submitted and everybody who got them. So congrats. All right, we're now on to the main event. Our speaker, Nathan DeLee. I was delighted that he was come over to give a talk. So I will hand it over to you. I don't have your entire resume. He's just awesome. Let's just. I've worked with Nathan on several things, and he's just fully awesome. So that's your resume right there. Now let's see what he talks about, where everybody is. All right.
All right.
Grandfather was a member of the American Astronomy Society. But then in mathematics, he was a 10-hour Einstein. But that's mathematics. That's another thing. But he did like American Astronomy Society.
All right. Okay, so our question for today is trying to understand, where should we be looking to find life in our solar system and beyond? Where is everybody, right? How are we on this little blue rock all by ourselves? Well, it wasn't always that way, right? I mean, certainly throughout human history, human beings believed that we were, in a very full world, right? There was, the trees had personalities and thoughts, and, there were, goblins and, gods and monsters and all sorts of things that would fill, every nook and cranny of our world. But slowly over time, right, we have, at least, in sort of modern America, right, we have the fairies and all that sort of thing have vanished, right? And now the only sentient beings that we really think about are human beings. And so in many ways, our lives have become much more empty. We've become much more alone. And so I think that may be partly why, as a species, we have a tendency to look out into space in the hope of finding someone like us, right? Another, entity or groups of entities to communicate with. And, this has been a problem, ever since we really had modern astronomy. And Enrico Fermi sort of captured this essential paradox that we seem to be existing in, right? So we know that the universe is big, right? It's very, very, very large. It has many, many stars in it, many, many galaxies. And it's old, right? 13.8 billion years old, right? So it's big and it's old. And yet, we've not seen any signs of other advanced civilizations, right? We haven't picked up radio signals. We haven't picked up, any indications of sort of non-natural phenomenon. So, what are the possible answers for this? One, maybe advanced civilizations are rare, right? That's a possibility. Why might they be rare? Well, it may not be the normal end of evolution, right? It's not clear that if the dinosaurs had been left to their own devices that they would have gone in the same direction we did, right? Minus, one ill-timed, meteor, right? We may have had a very different evolutionary path here on Earth. So maybe that's it. Maybe advanced civilizations are unstable, right? 1950s in particular, people were thinking about this a lot. Maybe all advanced societies eventually learn how to make nuclear bombs or whatever else, and they wipe themselves out. So maybe we just don't last very long, right? The second, and perhaps more optimistic point of view, is that we just haven't detected them yet, right? And the third is, maybe we're looking for the wrong indicators, right? We assume that life is like us, right? All examples of life on Earth, right, have a very common structure, have very common needs, and maybe we're looking in the wrong place. So in the end, the question boils down to, where is everybody, right? Where's our ETs, where's our Wookiees, etc. And again, this is a question, of course, that's held us for a long time, but if we go back 100 years, right, we can see sort of where the first sort of hardcore attempts to find life outside of Earth sort of begin. So we begin with the observations by Schiaparelli. He was the director of the Milan Observatory, and in 1877 he gave a couple papers where he talked about seeing linear features on the surface of Mars, which he used the word canali for, which means channels or canals, right? It can be translated either way. Well, you and I both know that if it translates to channel, we're like, well, channel, right? That's a natural phenomenon. But a canal, why, that is an entirely different sort of thing. Someone has to build a canal, right? And so that little bit of mistranslation, right, sort of started for this entire press to look for civilizations on the surface of Mars. And the person who really pushed this idea, who really, had the resources to really understand this, was Percival Lowell, right? So he had a scientific background. He was a world traveler. He'd written a whole bunch of treatises on Asia in particular. And he had enough money that he was able to fund the kind of instruments that you need to do this sort of search. So he heard about these canals, this canali, right? And he decided to build his own observatory. And so that observatory, Lowell Observatory, still exists today in Flagstaff, Arizona, and is still doing major scientific work. Now for him, he used the telescope at the Lowell Observatory to do observations of Mars. He also looked at Venus. People often forget that, but the thing that he's really known for is mapping the surface of Mars. And as a result, he ended up, creating all these maps, and he created several books, right, detailing what he saw on the surface. Now, what he saw, right, was not what other people saw, right? So other observatories with bigger telescopes were like, oh, this all looks kind of like geological formations. But he's like, no, this is an advanced civilization, right, that's pulling water from the poles down to the high deserts, right? And he came up with this whole thing about what was going on with Martian civilizations. And he speculated about what they were up to and all that. So this, of course, prompted a lot of people's imaginations, and so you get books like War of the Worlds and all that, right? This idea of Martians, right, suddenly really becomes this major cultural phenomenon. Okay. Well, maybe fortunately or unfortunately for us, we live now, and we know that there is no Martian civilization on the surface of Mars, right? We've sent rovers there, we've looked all over the place, and as far as we can tell, there's no advanced civilization there. So maybe we need to step back and ask ourselves, what are the requirements of life, right? If we really want to find life in the universe, how do we do that? Well, the way to figure this question out, or at least to find life that's similar to our own, is to look in the most bizarre places here on Earth. So we know that life can live in hot climates, it can live in cold climates, it can live near underwater volcanoes, it can live in acidic environments, it can live in alkaline environments, salty water, right? There's even life in the little bits of water suspended in the glaciers of Antarctica, right? So once life gets a chance, it spreads everywhere. It fills everything. We've even found life surviving in high radiation environments, right? So none of these will stop us, right? Assuming we have the right materials, right? So there's sort of three requirements that we've boiled down are necessary to have life, at least as it exists here on Earth. The first is you have to have a source of nutrients, right? All living things eat. They eat something, right? They have to be able to build their body out of materials that they get from their surrounding environment. The act of living, right? If we think of it, biologists, have their way of thinking about living, but, in astronomy or physics, we think about the use of energy, right? So there must be an energy source of some sort, right? You and me, we consume chemical energy in the form of food and drink, right? Plants, of course, can get their energy from the sun, but you have to have some sort of energy to have life. Finally, as far as we can tell, you need to have liquid water or some other solvent to be able to carry out the chemistry that needs to happen in order for life to exist. Okay, so these are the three things that we're looking for. And it turns out of these three, liquid water is the tricky one. That's the one that's actually hard to find in our solar system. Okay? So let's return to Mars. We have signs that Mars used to have significant amounts of liquid water. Right? So you see in this picture here that there is, ancient riverbeds. Right? There's clear signs of erosion. Right? And so we know that in the past, Mars had a lot of water, and of course, where there was a lot of water, maybe there was time, right, for life to form. Even now, there appears to be water underneath the surface of Mars, or at least there's indications of it, right? So here's an example where you see in the first picture, there's, just a crater, and then the second picture, taken a little later, there's this little bit of white that has appeared. Right? So you're on Mars, there's no one going around with a paint can, right? So what is kind of shiny and can just appear out of nowhere? Well, one of those things is water. And so the thought is that we had some sort of ice plug on top of the underground water. That ice plug fell out during a avalanche on the side of the crater, and then the water shoots out onto the surface and then of course immediately freezes. Other signs of water. So we have two crater impacts here. And you see they have something shiny in the bottom. Again, most likely water. And if we go again and again and again over time, we see that ice water sublimates away. Right? So there was water underneath the surface that was released by the impact, and then over time, it sublimated into the atmosphere. Again, it suggests that there is some present water on Mars. But Mars is not the only place that we can find liquid water in the solar system. Another option is a moon of Jupiter called Europa. So Europa is very far away from the sun, right? It's going around Jupiter, so it's way out there. And so the sun's light is not bright enough to produce the heat necessary to have liquid water. However, the moons of Jupiter interact with each other and produce, through tidal forces, internal heat that effectively melt the ice that would be in their cores and keeps a liquid water ocean available. Right? And so there have been plans made to go check it out, right? So the problem always was with Europa that, okay, we have a lot of indicators that there's liquid water somewhere underneath the surface of Europa, but is it, 10 inches under the surface? Is it 10 feet? Is it 10 miles? Right? It makes a huge difference, because if it's 10 miles, right, we're in trouble. Right? There's no mission that we could produce that's going to be able to go to Europa to find that. But that is not going to be something that we're going to have to do. That instead the water will come to us. So the Hubble Space Telescope observed a geyser of water shoot out of the surface of Europa. It was 200 kilometers high. What does this geyser tell us? Well, one, we were right, there's water underneath there, right? And two, there are cracks in the surface that are sufficiently deep to release that water from time to time. This particular event released something like 7 tons of water. And so NASA is interested in sending out a probe to, try this out. It's the Europa multi-flyby mission, and the idea is to have a probe that goes around Jupiter and sort of waits for the next geyser to show up. And when that geyser happens, to run through it and do all of our analysis on that. Now, so you say, okay, fine, there's liquid water on this, interior of Europa. Okay, there's energy in the form of heat, and chemical nutrients are easy to come by, right? Why do we think that life could survive in this sort of situation? Well, as I mentioned before, right, we know here on Earth life can live deep in the ocean, far away from the sun's light, right? In this case, you see here is an example of an underwater volcanic vent, and they have found extremophile life that lives near these vents and benefits from the heat that comes from it. And so there's a lot of reasons to think that if life could have gotten started on Europa, then it could in fact flourish in that environment, especially if you have a giant ocean, right, that covers a good portion or perhaps all of the underpart of Europa. Okay, so these are places where we could find life a lot like our own. But what if we want to push our minds a little farther? Right? What if we want to look at life that's not exactly like ours, but maybe behaves in a somewhat similar way? There's another place in our solar system we could look, and that's Saturn's moon Titan. So Titan is very cold, right? Minus 291 degrees Fahrenheit. And so there's no liquid water on Titan, obviously, right? But it has something else that might be able to serve the same role, and that is methane. So methane undergoes sort of the full water cycle, what we'd call the water cycle here on Earth, in the sense that it can evaporate, form clouds, and then rain back down to the surface. And methane is a solvent. And so it's not completely crazy to think that you could have a life form that exists in this sort of environment. Again, it's nothing like, if we're talking about any life on Europa would be completely alien in every way, right? It would be chemically different than us, down to its fundamental nature. But it's a possibility that there's something there. We'll have to wait for a future mission to find out. Okay, So these are things that are close to home, but, right, a lot of things we're talking about here would be probably, you know, microscopic life, right? If we're talking Mars, we definitely don't see large animals running around, right? So that's not quite as exciting, right, as what people really want, right? They want your, you know, advanced civilizations. So how do we go about finding those, or at least getting a rough handle on the number of civilizations out there? Well, there's a famous equation created by Frank Drake, which is really just getting out a napkin, right, and writing down the things that you think would go into figuring out how many advanced civilizations there are in the universe. So we have a couple of different things, right? So we have the number of habitable planets. We have the fraction of those planets that have life on them. The fraction of planets with life that evolve to advanced civilizations. And then how long do advanced civilizations last? Do they last 100 years, 1,000 years, 10,000 years, a million years, right? It makes a huge difference. If they only last 1,000 years, that's not much in the life of the universe. But if they last a really long time, then it's going to be a lot easier to find them. So step one is to figure out how many planets we have, right? If we don't have that number, the rest of those fractions are not useful. Okay, so let's get to that question then. How do we find planets around other stars? So we're going to try an eyesight test here for you all. Can you all see the firefly next to the spotlight? Anyone pick it out? It's hard, right? I'll make it a little easier for you. How about now? Can you find it? There he is, right? This is the fundamental problem that we have when we try to find planets around other stars. The difference in brightness between a planet and its host star is many orders of magnitude, and so is very difficult to sort of directly image planets. Now, it doesn't mean it's impossible. There certainly have been attempts, and with certain stars, it is possible to actually see those planets. So, for instance, here's Fomalhaut. If you look at this little zoom in, you can see that in this image, there's something going around Fomalhaut that moved from 2004 to 2006, right, on a Keplerian orbit. Right, so there's a little thing forming out there in that dust disk. Also around HR 8799 actually has 4 different planets. Now you notice these are pretty big planets. So this is 7 times the mass of Jupiter, right? So Jupiter is the biggest planet in our solar system, but it turns out that other solar systems, or other stellar systems if you want, right, have a wide variety of different sizes of planets. And so it turns out that if you want to, you know, find planets just by taking a picture of them, right, you really need sort of these big planets, and usually you're doing it around these pretty big stars. So the reason for that is it sort of forces the planets farther out, and so you can actually separate them from their host star. This again is not the type of star that we're really looking for. It's not, these are stars that are much hotter than the sun, and it's not necessarily, you know, what we're interested in, right? Because again, we kind of know, right? Well, we're kind of looking for us on some level, right? So how would we go about doing that? Well, we can be a little more clever, right? So we could take the Doppler effect, right? So we've all stood, you know, near a train track when the train comes, right? And we notice that if you listen to the whistle on that train, it has a different pitch when it's coming towards us and when it's going away. And it turns out that by measuring the frequency of that pitch, you can figure out the velocity and the direction that that train is going. Is it coming directly towards you, or is it coming directly away from you? So it turns out that all things that are wave-like in nature, so sound is wave-like, ripples in a pond are wave-like, but light is also wave-like, and so it also experiences the Doppler effect. And so when we have a planet going around a star, the gravitational pull of that planet can cause the star to wobble back and forth. So basically you have a mirror image on some level of the orbit of the planet around, right? So the planet has a big orbit, and the star moves in response to it, right? And so we can measure how that light gets bluer or redder. Bluer meaning it's coming towards us, redder meaning it's going away. And by plotting that up, we can figure out the mass and the orbit of that invisible planet. So here's just an example of how this would work. Again, we have our star, and we have our planet. And you see, as the planet goes around, the star wobbles, right, directly opposite, this is the center of mass of the planet-star system. And if you plot up the velocity that you measure, you get a very nice little sine curve, because this is a circular orbit. Okay. Well, this is kind of a clever technique, but for a long time, people were like, well, yeah, you can do this, but like, you know, trying to detect that on Earth would be very hard. You know, Earth's effect on the sun would be very, very small. Even Jupiter is so far away, it's just not a very big velocity. What we couldn't know at the time is that other solar systems do not always look like our own. So, back in the mid-1990s, we discovered that there was a very unusual solar system. Here's the actual data from that measurement. And you can see that we have a very clear signal, right? So this planet is around 51 Pegasi, and it has a very, very small orbit. And as a result, it has a very strong signal that we can pick up. In fact, this was such a major thing because, right, all of a sudden it said, oh, right, we can actually detect these planets around other stars. And suddenly a whole new field, basically, in astronomy came into existence. And so when you do that, you do get a Nobel Prize in 2019. So here's our planet. So we can see that it has a period of 4.2 days. Right? That's crazy. Right? I mean, that's nothing in our solar systems anywhere near that close to the sun. Right? Not only does this planet have a very, very small orbit, right? So you see in the picture, right? You feel, you know, you get the artist's conception that the planet is very, very close to its host star. But also it's a very massive planet, right? It's half the mass of Jupiter. So imagine you take something that's sort of Jupiter size and you push it down to the very center of our solar system. And of course that allows you to get something you can actually detect. Okay, so that's one way that you can detect planets around other stars. Another method is called the transit method. And in this situation, what you're doing is you're waiting, or you're looking for the sort of special circumstance where when you look at a star, you happen to have a planet move directly between that star and us. And so you start out here where the planet is not blocking the star. When the planet moves in front of the star, the light curve drops. And then when the planet moves off again, it pops back up. So it looks something like this. So there's our little planet. It's working its way across. And you get this very distinct dip. Now that's teeny tiny, right? Because the planet is very small compared to its host star. And so it's, you need very precise instruments to be able to find this. But if you do, you can figure out a lot about the orbit of the planet. You can figure out the radius of the planet. And that's a lot to give you something about what's going on. So to take advantage of this technique, NASA created the Kepler mission. And so the idea of the Kepler mission was to look at 170,000 stars and just stare at them, more or less continuously, for 4.5 years. Right, as I said, you have to have this sort of perfect alignment, right, between the Earth, the plane of the extrasolar system, and their host star. for us to be able to do this detection. Of course, as far as we know, planets are randomly oriented in space. Well, that's fine. If you just look at enough stars, then a few of them will by chance line up, and we can then start to figure out what's going on. And so the goal here was to figure out what the occurrence rate was of Earth-like planets around Sun-like stars. Now, fate oftentimes does not go according to plan. It turned out that it was actually a little harder to find Earth-sized planets around stars like the Sun, and I'll talk a little bit more about that in a moment. But they did manage to have a pretty good survey, right? So it was on Sky for 10 years roughly. They looked at 500,000 stars. They got, as of this point, 2,600 confirmed planets. They also found a bunch of other things, right? Supernova, etc. Right? And so, we made some progress. It turned out that there was a mechanical failure that occurred earlier than we hoped on Kepler. And as a result, we had to move from the original survey, which was to look at a single piece of sky for, well, it was supposed to be 6 years. It became 4.5. And instead, we started going along the ecliptic, basically using the sun to help stabilize the orbit of the Kepler spacecraft. And so we end up getting stars spread out across this line here. Okay. So for all that work, what did we get? So here is a plot of orbital period versus size relative to the Earth's radius. Okay. So of course the thing that we're most interested in, okay, here's Earth. All right, we're doing good. Okay, we're going along, we're going along. How many days are there in a year? 365, right? So that's, it's here, right? So it turns out it's actually pretty hard to get a detection of an Earth-like planet around a Sun-like star in an Earth-like orbit. Because basically you want to get something like 3 transits, right? Well, it takes a year for the Earth to go around. If Kepler is only running for 4.5 years, right, things have to be pretty perfect for you to be able to find that. And so instead, what we found, instead of finding an exact Earth analog, we found a bunch of other things, right? A bunch of other types of planets that we really hadn't thought about in detail because, until you sort of know they exist, right, you're not really sort of focused on them. And so we get rocky planets like the Earth. There are rocky planets right next to their sun, so they're really lava worlds, right? You get worlds made of water and ice, and of course you get hot Jupiters, and then the cold gas giants like we're familiar with. When you get the chance, I would suggest that you try out looking at the Kepler Orrery. This is sort of, they have several of these, and I'll go ahead and show you one here. Let's see if we get lucky and everything works. Oh, it looks like we're going to be okay. There we are. And so you can see all these different types of solar systems, right? With big planets, little planets, different temperatures. Note that this is our solar system, right? Mercury, Venus, Earth, Mars, Jupiter's out here, I believe. Right? So these are all teeny tiny because Kepler is very good at finding smaller solar systems. And my point with this mostly is that the diversity of solar systems out there is amazing, right? There are all sorts of things that we just really didn't envision existing. And of course, well, they're there, and now we have to try to explain them. Of course, that's one of the fun things of science is we have our theories, we think we know how solar systems form, and then you go out and you get that data, and then suddenly, bam, you're hit with something that's just fundamentally different than than what you were expecting. All right, so let's see. Hey, it worked. Okay. All right, so I suggest spending a little time with that orrery because there's a lot of interesting stuff going on, and you know, again, there's I think they're up to maybe 5 or 6 now. So, anywho, all right. So, the Kepler space mission was designed to, you know, figure out how many Earth-like planets there are around Sun-like stars. And, you know, there's various analyses that have been done. This was a relatively early analysis that came up with something like 22%. But as you noticed, right, our data was incomplete. We didn't actually find a bunch of Earth-like planets around Sun-like stars, not because they don't exist, but because our detection techniques were not sensitive enough to find them. So this is based upon extrapolation on the planets we were able to find. All right. So maybe we can't find a place exactly like home, right? Maybe we can find something that's close, right? So there are other types of stars that we can look at. As you noticed, a lot of the solar systems that Kepler was able to find were small. So here's our solar system, and this green area represents the habitable zone, the zone where liquid water would exist. But if you look at a star with half the mass of the sun, that habitable zone moves inward, and a tenth, even more inward. And so if you're looking at stars that are much less massive than the sun, you have a pretty good chance of finding a planet in the habitable zone. Now, as I mentioned, with the transit technique, you can get the radii of the planet if you know the radius of the star. And we have, you know, reasonable models of the radii of stars. And so you can figure out things about the composition of the planet based upon its probable mass and its radius. Usually if you want the mass of the planet, you have to use the Doppler technique that I talked about before. So if you can combine the Doppler technique and the transit technique together, then you can actually say a lot about what's going on with this planet. And you get very different types of planets, right? So you could have things that are made of pure iron up to things that are pure hydrogen, right? Something more like a Jupiter sort of planet, and then, you know, things that are more like a Mercury. And then, of course, you can get all sorts of things in between, right? So again, not only is there a diversity of solar systems, but there is many different types of planets that you can get around these solar systems, and we can figure out information about those planets. So just some example of systems that Kepler has found. So Kepler 186 has a planet, Kepler 186f is in the habitable zone. And Kepler 452, the same thing. And again, if you just compare those habitable zones to our own, right, you can see that, you know, especially in this case, it's, you know, sort of much smaller, right? So this is the kind of system that you'd expect to see. And again, the habitable zone, again, just means a planet that could have liquid water on its surface. Now, of course, there's a lot of complications on exactly how you calculate that habitable zone, right? The atmosphere of the planet makes a difference. But this is sort of a rough back-of-the-hand calculation of what that would be. Okay. If you have different types of stars, right, from something like the sun to something hotter than the sun to something cooler than the sun, right, you can have habitable zones in different areas, right? You have different amount of light reaching those planets. And so again, depending on the model of your atmosphere, you know, you might say, you know, maybe this is your habitable zone, or maybe it's narrower if you assume that the atmosphere is similar to ours, right? Again, there's a lot of sort of dials you can turn on this. But the point is that there is a lot of stars that start to fall, or planets, I should say, that fall in these habitable zones, and thus we start to have hope that we could find life on these planets out there. Okay. All right, so we find these planets. Doesn't get us to where we want to be, does it? Right? We don't, I mean, planets are nice. Everyone likes planets. But we want to go that extra mile, right? How do you figure out whether there's life on that planet? Well, if there's an advanced civilization and it's flashing lights at us, that's great. Problem solved. But maybe we're not going to be so lucky. Even our own civilization doesn't necessarily produce all that much civilization noise, if you want. Right? So there are things that we can look for. Well, one thing you can do with a transiting planet is you can sample the light that passes through the planet's atmosphere as the planet is transiting its host star. And it's a very tricky technique and hard to do, but in some cases you can look at what the atmosphere contains. Basically by taking a prism, spreading the light out from the star, you can see individual elemental signatures, or in this case, molecular signatures. Right. So most planets in our solar system look like this, like Mars. Right? You have a lot of carbon dioxide in the atmosphere. Same for Venus, a lot of carbon dioxide. But if you look at Earth, it has carbon dioxide just like the other two. But you can also pick up this strange little line of ozone. And the reason ozone's interesting, O3, is that ozone is often created through a process of high energy light interacting with O2, the oxygen that we breathe. Now it turns out that oxygen is very reactive, right? So we think often about the surface of Mars being red, right? Well, that's because there's oxidation of the rocks, right? The oxygen that could have been in the air has long since, been absorbed by the surface of Mars. On Earth, there are things that push oxygen back into the air. Anyone want to tell me what those things are? Plants, right? Plants and algae and all that sort of stuff. Things that photosynthesize, right? Push free oxygen into the air. And so, of course, Earth is unusual because it has this signature of free oxygen. And this is exactly the sort of thing we need to look for, because oxygen, again, is not something, at least there's no sort of well-known method of producing oxygen without life. Right? So if you can find oxygen, then that is you've got a pretty good chance that there's some sort of life on that planet. All right, so Kepler has sort of reached its end, and so what are sort of the next step? Well, I personally have been involved with the TESS satellite, and what TESS wants to do is look at a large sample of nearby stars and get a sense of what the local census of planets looks like. So just to give you a sense, right, Kepler was looking at a single piece of sky, and they were looking deep into the galaxy, out to 3,000 light years. TESS, on the other hand, is going to try to look over much more of the sky, but be centered in on our local neighborhood. And so they've been running for a few years now. And here is a picture of sort of the cap here, which is assembled from each of these sort of 4 cameras that they use on the TESS satellite. And so they basically go strip by strip by strip, and they look for transiting planet signals. And then they work their way across one part of the one part of the sky, and then they flip over and they look at the other part of the sky. So far, we've looked at 42 of these strips in the sky, again, looking for extrasolar planets. Recently, since the TESS satellite's still going strong, they've taken the satellite and they've flipped it on its side so they can take images of the ecliptic. And so these are just some pictures of where they're going to look. And you notice that these fields all have Ks in front of them. They have Ks because they were Kepler fields. And so we're going to be able to go back and look at transiting planets with tests that were originally found with the K2 program. And here's just another set. So far, we have found 2,869 stars with Kepler and or I should say planets with Kepler and K2. And with tests, we're up to 156 and counting. This is just a little plot that I made with the number of confirmed planets as of Wednesday. So this is Jupiter radii. This is orbital period. You can see this goes pretty far out. So this is the 4,525 confirmed planets. Again, we're more interested in a very particular type of planet. So let's zoom in a little bit. Now this is Earth radii and orbital period. And you see we are starting to get things that are getting closer, to this sort of Earth-like area. Still, the bulk of our planets so far, right, are down here, right? So if you want Earth-sized planets, they tend to be closer to their host star. But we're making progress. And so I'll leave you with this thought that what we know today that we didn't know in the early 1990s is that the universe is filled with planets, and some of those planets are in the habitable zone. And so there's a lot of places for us to explore out there, and there's a lot of chances that we find something really interesting. Thank you.
Hi, I'm on this, the transiting method. I know that there are a lot of people looking with Earth-based telescopes.
Yep.
How do you take into account the atmospheric distortion and the variability of the stars themselves when you're looking at the transiting method?
Yeah, so the secret to this is something called differential photometry. Basically, you take an image of a field with the star of interest, and you compare it to all the other stars nearby. And you take, image after image after image after image, and what you do is you basically compare the light from your science star to these standard stars, which you assume are not variable. And by doing that, you can get rid of a lot of the issues with light pollution, variable atmosphere, all that. I have a student right now who's taking data with our 14-inch telescope on top of Founders Hall at Northern Kentucky University, which is in the suburbs of Cincinnati. And we are able to detect transit dips. It's really amazing. You're like, is this going to work? It works. It's really quite astounding. I believe you guys have folks doing work, doing follow-up of Kelt here as well. So
I have the microphone, so I guess I get to ask.
Sure.
Now I forgot my question. Have we been able to look at stars and say that there's almost certainly not a planet around certain ones, so we can kind of put an upper and lower limit on what may and may not be there, or how many planets there might be?
Yeah, so this is the tricky problem when we're trying to come up with a census of solar systems in the universe. And that is that both the Doppler technique and the transiting technique really depend on planets being relatively close to their host star. And so it is often very difficult to say with any certainty whether there are no planets, right? You can say that there are no planets in certain locations with respect to the star, right? You don't see an RV a Doppler variation. You could say the star is flat to this precision level, but if you move, if a planet slightly farther outside of that range, then you wouldn't be able to discount it. And with the transiting method, right? I mean, we know that we're missing most of the planets, because they have this random orientation and only a very small fraction are going to be lined up perfectly. But what we can do is, because that is a random orientation, you can mathematically work out, based upon the planets you do find, how many you were missing. So that's, that's nice. So it's very hard to say, no, this star does not have a planet. Really what we can do is say this planet, or this star does have a planet. Yep.
Any more questions? Oh, come on.
Students in my 307 and 507 class, I would love to hear questions from you.
Dun, dun, dun.
The gauntlet has been thrown.
Extra point.
You run well. So I recently thought I saw that there was a rule of thumb that says X percentage seem to have planets.
Right.
What was that number?
So I think the rough guess is that most stars have planets. If you're interested only in Earth-like planets, right, the 22% number that I gave is there. But if you're just interested in any type of planet at all, I think the rough rule of thumb is that it's like 1 planet per star at least. Right? And again, that's a lower limit because of the problem we just discussed, that we can detect them, but we can't rule them out. Yep.
So earlier you talked about there may be other forms of life that are of a different chemical composition.
Mm-hmm.
Do you think that any of our detection methods that we have today would be able to see that?
So that situation is trickier because, if we make the assumption that photosynthesis, right, is the way that you're going to, have life, and thus you produce oxygen in the atmosphere, that method would not work for detecting life on, let's say, Titan, for instance. And so really that comes down to sort of an astrobiology question. Can you come up with a plausible model of life based on a methane, some sort of methane, chemical series? And what are the products of that type of life? And I personally don't know of where they've gotten to on that and whether or not those products are distinct, right? Because if the answer is it produces carbon dioxide, well, then you're in trouble. It's not useful, right, from the detection standpoint. If it's something unusual, right, something you wouldn't expect in an atmosphere, then maybe we could. But I think there's still a lot of work to be done. And I know that there are several graduate programs that specifically try to combine astronomy and biology together to be able to answer those sorts of questions.
Do you know if there are any efforts being made to measure exoplanets with the Vera Rubin Observatory?
So yes, I know that there have been papers put out talking about how you would try to find transits, using that observatory. Because as long as you have some transit, as long as you have some photometry, you have a chance of doing something. I know that they were arguing about the cadence that you would need, and so I can't remember whether it's, there's sort of the general cadence and then there are specific cadences that they follow. But I do know that there is work being done on that, yes.
Is James Webb going to put us in a situation where we can actually measure kind of what we're looking for?
So that transmission spectroscopy that I talked about, looking at the atmosphere of a transiting planet, that's relatively difficult to do in the optical. But because the James Webb operates in the infrared, the difference in brightness, right, between the host star and the planet is much less. And so it should be easier to do this sort of transmission spectroscopy using James Webb. That's one of the things they'd like to do. Because basically how it works, right? It's sort of a simple concept, right? You take a picture of the star, right, without the planet in front of it. Then you take a picture of the star with the planet in front of it, and you subtract the two. And what's left over must be the planet, right, instead of what's in the atmosphere of the star. Well, all things that are simple also have, in theory, can be very difficult in practice, right? And so when there's a huge brightness difference, it can be hard to do. But James Webb, is a very powerful piece of equipment, and it's working in the infrared, and so it has a very good chance of being able to sort of open up, that kind of analysis much more than what's been possible so far. Yeah.
Does that scope also have a coronagraph?
Repeat that question.
Yeah. So the question was, does the James Webb telescope have a chronograph? As far as I know, it does. Yeah. So that would be, you don't need a chronograph for that particular measurement, but if you want to do direct imaging, then yes, you need a chronograph to do it. A chronograph, just as a quick aside, is when you use a technique to block out the light of the host star so that you have a chance of seeing the light coming from the planets. So the two images that I showed you, right, of direct imaging of planets around stars use chronographic techniques, right? One, I think, actually used a physical device to block it out, and the other one used a fancy filter, effectively, to cancel out different modes of the light to be able to get rid of the starlight. So there are, chronograph technology itself, right, is a whole rabbit hole you can go down. There's a bunch of different ways you can do it. And there's kind of a lot of exciting things you can do with that. Yeah.
Over a year ago, there was a discovery of some organics in the atmosphere of Venus.
Yes.
And that really got me interested, and I asked Dr. Kilcoff about it, and he told me that he thought Venus was understudied. Are there any efforts to further investigate that you know of?
Yes, I believe there's another mission getting ready to head to Venus relatively soon. And hopefully they'll be able to sort of push our understanding of that a lot more. I mean, Venus is a tricky beast to study, right? You go, boy, we keep sending our robots to Mars. Well, that's because Mars is relatively nice, right? It's nice for our robots. They have a little bit cold home, but it has some light, it has some dust storms, so everything's okay. Venus is, as we know, is a very hot place, right? You can melt lead on the surface, and it has the, sulfuric acid rain and all that. So it's tricky to send things there. So we've studied it a little bit less as a result. But yeah, I can't remember the name of the new mission out there, but yeah, I believe it was just approved very recently.
Two have just been approved, Venus Express and one to tag along. So they're actually, NASA's doing a double one on Venus now. So it's...
Yeah, and of course, again, with the idea of extremophiles, we know that Venus, in many ways, looks like the Earth, right? If you were just to look at our solar system and say, which planet is the closest Earth analog, Venus is the closest Earth analog, right? Mass-wise, size-wise. And so it would not be totally unreasonable to think that it had a very Earth-like history up until everything went nuts, and the temperature increased. So it was once much like the Earth. And so the question is, did life have a chance to get its little fingers into things? I don't know if it has fingers, but you know what I mean, right? Because we know that once life gets going, I dare you to try to stop it, right? Once it's there, it's there. And so, maybe Venus has something for us.
Back here.
Yep. Oh.
Is there a known temperature cap that life can survive in to be detectable for us?
Right. So, those are two different questions, right? Is there a temperature cap above which life can't survive? I don't know what it is. I mean, obviously we can sterilize things if you get things hot enough, but I don't know what the cap is. Obviously, things like spores or, microscopic water bears can take quite a lot of punishment, but I don't actually know what the number is. The second question is, the life that's hardy enough to survive those situations, do they produce a detectable signal? And that, I think, is fairly unlikely, but again, there could, maybe we find that there's a photosynthesizing, water bear, right? And I'm not talking about bears, I'm talking about these little microscopic animals that kind of look like bears, vaguely. In any case, yeah, maybe there's something like that that actually photosynthesizes in large amounts, right? I mean, for instance, if you ask where did the oxygen on Earth come from, well, blue-green algae, right, was producing oxygen on Earth long before plants got in the game, right? Plants are relatively new, all things considered. And so, is it possible that you could combine something that photosynthesizes with being, a hardy little critter? I don't see why not. But then I'm not a biologist, so I can envision a lot of things. Yep.
So you mentioned detecting planets using transiting and Doppler. Are there any other methods of detecting planets that are not like right next to the star or very large?
Yeah, so the direct imaging works much farther away, but only works with a very limited class of stars. Another option is microlensing. This is where you use Einstein's equations of gravity to basically measure the distortion in space and time caused by the gravity well of a planet around its host star. That can detect planets farther out. The problem is that those tend to be one-time events, and so it's hard. You get a signal when it happens, and it's then very difficult to come back and get additional information about it. So I think, yeah, those are the four major. So there's another technique. Let's say that you find your transiting planet. Getting back to your question to some extent, if you have a transiting planet, you can sometimes detect whether it has buddies that you can't see, right? Imagine that instead of the orbital plane of that particular solar system being dead on, what if it was tilted just a little bit, right? So you see maybe an inner planet, but you can't see the outer planets because the angle's wrong. Well, there's a technique called the transit timing variation technique, where you have your planet come around, and it's supposed to be regular. It's supposed to be, you could set your watch by it, right? But sometimes you can't. Sometimes the planet's a little early, and sometimes it's a little late. The only reason a planet might be early or late is if there's another planet that you don't see tugging on it, right? So in the way that Jupiter tugs on us, to some extent, you can imagine other planets tugging on the planet you can see. And so this transit timing technique is pretty good for actually getting more complete solar systems when you only see a few of the planets. Yeah. I think I think there are a few others, but those are the main ones. Oh, yeah. Oh. So, but we'll leave it there.
Sorry, Dr. Hilverda. So obviously, like, this is a very observationally heavy field. It has to be. But I was wondering if there are any simulations that are playing a big factor into exoplanet discovery.
Oh, sure. So there's a lot of people who work just on exoplanet atmospheres, right? So, okay, if I know the mass of the planet, I know the distance away from its host star that it is, and so we have a rough sense of the surface temperature. You might even be able, if you have Doppler information, you might be able to get a density. So that means you have a rough composition. And so from that, you can simulate an atmosphere. Of course, there's a lot of, so one of the questions that I often am thinking about is how do you recover an orbit based upon the observational data? Because unless you're taking data constantly, right, usually your data is spread out over many days, or maybe weeks or months or years. So maybe you get an observation, in March, and then another one in April, another one in July, and another one in September. Okay, how do you take those, right, obviously those are oftentimes multiple orbits. How do you reconstruct the correct orbital period from that. And so, there's a lot of work that goes that way as well, as trying to actually analyze the data in a useful fashion. As I mentioned, there was the cadence work, right, trying to figure out what cadence you need to return to a planet to have your best chance of finding it. Yeah, of course, there are people who are very interested in the geology of these sorts of planets, right? Okay, what if your planet is more or less made out of water? Right, so you have a planet that forms near the ice line or something like that, but never quite gets big enough to become like a Jupiter, right? Well, what do you have then, right? So I think there's a lot of theoretical routes you can go. And of course, there's the big question: here's my observational data. How do I transform that into an actual census of the planets in our area? So, yeah, there's if you go to AAS, there are entire rooms devoted to more theoretical pursuits. Yeah.
This isn't exactly like an exoplanet question. Can I still ask it though?
Sure.
I'm almost there.
You can just repeat your question. There you go.
So, in these star systems, we can't track that, but do you think that there's having plasma oscillations at their heliopause like we are here in ours?
Ooh.
Or is that even something that we can consider since it's quite new to us?
Yeah, I mean, I think, I suspect that the level of detection that you need to actually be able to answer that question is tricky. Now, you can model it, of course.
Yeah.
Right? So based upon our measurements, right, the heliopause in our solar system, you can get a sense of what a sun-like star does. But I don't know. Yeah, I think it would have to be theoretical work for the most part. I don't work in it in particular, so I can't say it. Maybe there's someone who's come up with a very clever way of doing it. But
Yeah, I just thought I'd try.
yeah, sure. No, it's always good to see.
So for the transiting ones, how can you tell the difference between a planet actually transiting and if it's just a sunspot?
Ah, yes. So notice I use the word confirmed planets. There are many candidate planets that these transit surveys find because there are a bunch of different things that look like transiting planets. So you can have spots, for instance, especially if you're looking at a M dwarf star with these red dwarf stars. They can have spots that cover, the sun has, little spots all over the place, but a spot on an M dwarf can take up an entire half of the star, right? So it can be significant. Another major issue is binary systems. So let's say that you have the star you're looking at, and you have a binary system behind it. The light from this star, right, they just happen to be lined up. The light from this star can fill in the transit. So instead of looking like a binary star system transiting, it looks like a planet transit. And so there's a bunch of different ways that you can try to get rid of these false positives. With spots, the nice thing is the spots oftentimes have a color component. So if you take a look at the light curve in different color filters, a red and a green and a blue filter, you will see a difference in those light curves because the spots have an intrinsic color to them. Whereas a planet crossing should have no, it's just, it's a rock or whatever going in front of the star, so it should not have a significant color term. So that's how you get rid of spots. If you want to deal with various types of binary stars, there's a couple ways you can do it. If it's a bright enough star, you can use the Doppler technique. The nice thing is that most nearby transiting planets, if it's close enough to transit, it's close enough to get up a decent Doppler signal. And there, if it's a binary star, right, instead of having your, nice little planet, you have instead of meters per second or tens or hundreds of meters per second, you have kilometers per second, right? You're like, it's a binary star, right? In fact, that's something that I've worked with folks who've done that kind of work. Another option that Kepler has used, and TESS may try to use it to some extent, is you look at the distribution of light image to image, and if it's a binary star system, because you actually have additional sources of light, the center of the light, right, if you just add up the light and try to find the average position of the light, it oftentimes will move around a little bit if it's a binary system as versus a planet. You know, planetary systems, there's no additional light other than the star and then the little planet's reflected light. And so that's another way that you can try to confirm it. Yep.
Any more questions? Thank you all for coming up with excellent questions, because yes, these are all the issues that we face, and if you want to really make an astrophysicist cry, you say, what about magnetic fields? So that's, that was an excellent one.
Well, the Europa mission, in fact, is designed to avoid the magnetic fields of Jupiter. They're so destructive to the equipment that they have to put on a highly elliptical orbit to try to keep away from Jupiter until the right moment comes along. So.
All right. Well, in that case, no more questions? You sure? You can also come up and ask then. Thank you all so much for coming. Thank you for the speaker for giving us an excellent talk, and thank you for Laurie for sponsoring us for all these years. Thank you all.